Lesson 5, Equivalent Exponential Expressions. This lesson will be about how we simplify exponential expression involving different powers as well as radicals. A big theme that we talked about in Unit 1 was equivalency. You may recall, two expressions are equivalent if one of the following is true. Firstly, they simplify algebraically to give the exact same expression. Secondly, they produce the same graph. Let's explore this in example 1. We're going to begin by considering the parent exponential function, f of x equals 2 to the exponent x. We're going to graph that along with the following two transformations. G of x, which is 2 multiplied by the parent function 2 to the x, and h of x, which is 2 to the exponent of x plus 1. This would be a good time to pause the video, create the three tables of values, and graph the three functions on the grid using three different colored pens. When you're ready, click play to resume. Okay, here we go. So for the parent function 2 to the x, I'll generate the table of values. Let's plot those points on the grid provided. And there's our parent function f of x. For the function g of x, notice in the table I gave you the same x values. We can use our mapping rule here. We have an a value of 2. So to get the new y values, multiply all of the previous ones by 2. Let's do that. And I'll plot those points on the grid. Only plot what you have room for. And that will be the function g of x. Finally, for h of x, I didn't include x values here, but let's think about it. In this case, we have an h value of -1. That means we're moving everything to the left by 1 unit, so I'm going to take the x's in the previous table and shift them to the left by 1. And then, to get the y values, you could recognize that we're not changing the y values at all, meaning we're not vertically stretching, compressing, or reflecting them, and we're not moving them up and down. So the y values are the exact same from the first table. You could also verify this by plugging in the new x values into the equation for h of x, and you will get these y values. I'm going to go ahead and plot them on the grid provided. So we've got -1, 1, 0, 2, 1, 4, and 2, 8. And you're going to notice that the points overlap. So the purple function here overlaps with the red one, so this is g of x as well as h of x. And something very strange happened. Notice that the functions g of x and h of x overlapped. That would suggest that they're equivalent. Let's look at this in more detail. Example 2 is asking us to investigate this a little further. So as we already mentioned, the two functions were equivalent. Let's write that down again for completeness. And the reason for this, as I wrote down, is because they produced the same graph. We can also show that they're equivalent algebraically. For instance, consider g of x. This is equivalent to 2 multiplied by 2 to the x. But the 2 is really to the exponent 1, and you can use your exponent rules that we reviewed in lesson 1. When you're multiplying powers of the same base, keep the base and add the exponents. And in doing so, you're going to notice that this is exactly the same as the function h of x. So here we've shown two different ways why these functions are equivalent. But this actually leads to something else I'd like you to recognize. What type of transformation are we doing in the function g of x? So here we have an a value of 2. That means vertically stretch the parent function by a factor of 2, and then consider h of x. In this case, we have an h value of -1, so that means move the function 1 unit to the left. So in the case of the exponential function, a vertical stretch by a factor of 2 is equivalent to a horizontal translation by 1 unit to the left. Let's make a note of that. So please keep in mind this isn't always true, it's just the case for the function 2 to the x. And this is what this lesson will be about, equivalent exponential expressions. We're going to continue to explore this in the examples that follow. For instance, in example 3, we're asked to write 8 to the exponent x as a power of 2. So let me demonstrate this first example. Consider 8 to the exponent x. The base is 8, the exponent is 2. Here we're being asked to write it as a power of 2. And to do this, think about how you can write the base of 8 perhaps as a power of 2. Well, one way to do this is to recognize that 8 is equivalent to 2 to the exponent 3. This is because 2 times 2 times 2 is 8. So I've just replaced the base of 8 with 2 to the exponent 3. I hope that step is clear. You're allowed to make that substitution. And now that you've done that, you can use your laws of exponents on the right side. We're going to use the power of a power rule here, which tells you to multiply the exponents. So 8 to the exponent x is equivalent to 2 to the exponent of 3 times x. And that's how we were able to write 8 to the x as a power of 2. Let's continue practicing. Is it possible to write 64 to the exponent of 3x plus 1 as a power of 4? Well, yes, indeed it is. Let's begin by writing out the expression. Now, most of these problems involve manipulating the base. Can you write 64 as a power of 4? Well, certainly you can. 64 is equivalent to 4 to the exponent 3. So once again, I've just replaced the base of 64 with 4 to the exponent 3. All right, carrying on, we have to simplify the right side, so we'll use our power of a power rule here. Remember, that means multiply the exponent. So I'm explicitly writing out multiplying the exponents. And then you can simplify the exponent by distributing the 3 into the brackets. Final answer being 4 to the exponent of 9x plus 3. And that's how we've succeeded in writing this expression as a power of 4. Okay, in example 5, we're asked to show that 4 to the exponent of x take away 3 is the same as 2 to the exponent of 2x minus 6. With questions like this, where you're trying to show something is equal to something else, you're welcome to choose any of the two to start with. Let me show you what I mean. Let's begin with 4 to the exponent of x take away 3. You're trying to write something with a base of 4 as being equivalent to something with a base of 2. In order to do this, replace 4 with a power of 2. 4 is equivalent to 2 to the exponent 2. And then to further simplify this, you can use your power of a power rule. Keep the base, multiply the exponents. And then as we did before, distribute the 2 in the brackets. And we've shown that 4 to the exponent x minus 3 is equivalent to 2 to the exponent of 2x take away 6. While we're here, let me show you another way to do this. Let's say you decided to start off with the power of 2. You're able to do that as well. It can be a little more difficult to go from a smaller power to a bigger power, but here's how we do it. We begin with the expression 2 to the exponent of 2x take away 6. We'd like to write this as a power of 4. You can't just magically square the 2. You have to work with what you have. What you can do, though, is recognize that there's a greatest common factor of 2 in the exponent. Factor it out. In doing so now, we can use our laws of exponents once again, but this time sort of in reverse. Using the power of a power rule in reverse, you see that the exponent consists of 2 multiplied by x take away 3. We were told when you have a power to a power, multiply the exponent. So run that rule in reverse. This is like 2 to the exponent 2 to the exponent of x minus 3. If that's a bit confusing, I'm just using the power of a power rule in reverse. Then inside of the brackets, 2 to the exponent 2 is 4, and now all of that is to the exponent of x take away 3. So what I'm trying to demonstrate here is you're able to work both ways. If you ever get a question like this, just pick one of the two expressions and try to work with it to make it look like the other one. In my opinion, it's usually easier to go from a bigger power to a smaller power rather than the other way around. But hopefully this showed you both ways work. Let's try another one. This one is a little more complicated. We have to show that 1 over 3 to the exponent of x plus 2 is equivalent to 1 over 9 multiplied by 3 to the exponent of negative x. Recognize that the first expression has a fractional base and the second one has a base of 3. One trick that we can do is work with the expression that has a base of 1 over 3 and simplify by using the reciprocal rule. If we were to take the reciprocal of the base, then that makes the exponent negative. The base just reduces to 3, and distributing the negative sign, we have negative x take away 2. I just distributed the negative to both terms inside of the brackets. But keep in mind this is still the exponent. All right, we have the same base now. So this is good, but it still doesn't quite look like the expression we're trying to show. We need to get this 1/9 factor. What I can do is again use my exponent rules in reverse. Recall, when you're multiplying powers with the same base, keep the base and add the exponents. If we were to run this in reverse, we would take our exponent of negative x take away 2 and write this as a product of two powers, like this. Now, that step was probably a bit confusing, but just keep in mind I'm using the power rule in reverse. So notice we have the 3 to the exponent of negative x, like we did in the expression of the question. We just somehow need a factor of 1/9. Well, the good news is 3 to the exponent of negative 2 can be written as the reciprocal of a positive power, like so. By taking the reciprocal of the base, the exponent becomes positive. This works out to 3 to the negative x multiplied by 1/9. And since the order of multiplication doesn't matter, this simplifies to 1/9 multiplied by 3 to the exponent of negative x, which is the expression we were trying to show it was equivalent to. So that's done. We're just using exponent rules, but sometimes running them in reverse. This one we're just asked to simplify. So in the numerator, we have something with a base of 32. In the denominator, something with a base of 8. You can't just divide the 32 and the 8. So in order to simplify powers, they have to be the same base. Are we able to write 32 and 8 to a common base? And the answer is yes. 32 can be written as 2 to the exponent 5. 8 can be written as 2 to the exponent 3. Now both of them have the same base that will allow us to simplify the exponents, you'll see. Use your power of a power rule in the numerator. Use the same rule in the denominator. Remember, that just means multiply exponents. All right, let's go ahead and multiply the exponents of the numerator and denominator. And now that your bases are the same, keep the base and subtract the exponents. I'll write this out explicitly. And now you just collect like terms in the exponent of this expression. Final answer after collecting like terms is 2 to the exponent of 14x take away 30. And that would be a suitable final answer. Sometimes you might see an answer written factored. So what I mean is, in the exponent, you can see a greatest common factor of 2. So occasionally you may see it written like that. So I'll just show you both ways. If you ask me, both answers are acceptable. Okay, moving on. Couple more to go, so let's continue practicing. We're asked to simplify the following expression. This would actually be a good time for you to pause the video and try it on your own. The technique is very similar to what we did in example 7. So please try it, and when you're ready, click play to resume. Okay, here we go. We've got bases of 2, 8, and 16. Let's write all of these powers to a base of 2. The first one is already done, so just rewrite it. Instead of 8, replace the base with 2 to the exponent 3. And for the denominator, 16, replace that with 2 to the exponent 4. For questions like this, you'll always be able to find some sort of a common base. Now in the numerator, we have 2 to the exponent of 4x plus 1 multiplied by 2 to the exponent of 3x, take away 15. I just used the power of a power rule, and I'll use it once more in the denominator. That's 2 to the exponent of 8x plus 12. In the numerator, you're multiplying two powers with the same base, so keep the base and add the exponents. Keep the denominator the same for now. Let's simplify the numerator by adding the terms in the exponent. And we're almost there. Now that we're dividing two powers with the same base, keep the base and subtract the exponents. Almost there. Collect your like terms and you're done. So 7x take away 8x is negative x. Negative 14 take away 12 is negative 26. In most cases, this would be a suitable final answer, but notice that the exponent is negative. So we can definitely simplify this by pulling out a factor of negative 1. And as you know, it's never a good idea to keep your answer with a negative exponent. So let's take the reciprocal of this, which will write it as a positive power, like so. Okay, everyone, and that would be a suitable, fully simplified final answer. This one is a little different. Once again, we have to simplify, but look at what we have here. We have 0.2 multiplied by this fraction containing different powers. So how on earth do we deal with the 0.2? Well, first off, let's consider the bases of 125 and 25. Can you write those to a simpler power that they have in common? And the answer is yes. 125 can be written as 5 to the exponent 3. 25 can be written as 5 to the exponent 2. And here's the trick. 0.2 can be written as 1 over 5. And that's how we succeed in writing everything as a power of 5. This is really 1 over 5 to the exponent 1. All right, let's continue simplifying. In the fraction, we'll use our power of a power rule. So go ahead and multiply the exponents. This will give you 5 to the exponent of 9. Take away 6x. And that's over 5 to the exponent of 8x, take away 2. Once again, just using the power of a power rule. Next, we can go ahead and simplify the fraction. So we're dividing powers. That means keep the base and subtract the exponents. Okay, let's continue to simplify. So that's 1 over 5 to the exponent 1 multiplied by 5 to the exponent of negative 6x take away 8x is negative 14x. 9 take away negative 2 becomes 9 plus 2, which works out to 11. This power of 5 is technically over 1, so we're multiplying fractions. That means multiply numerators and multiply denominators. And lastly, you're dividing two powers, so keep the base and subtract the exponents. Final simplified answer, 5 to the exponent of negative 14x, and the 11 and the 1 subtract to give you positive 10. This is probably a good final answer. I would accept this one, but something else you can do is factor out a negative from both terms in the exponent. And then take the reciprocal of this negative power. So another way to write this would be as follows: 1 over 5 to the exponent of 14x take away 10. In this case, I would actually accept either of these two answers that I'm highlighting, and the reason is only one of the terms in the exponent of the first expression was negative. So if you ask me, both should be acceptable. All right, everyone, so that's going to wrap up our lesson 5. Once again, some recommended homework from the textbook. Try it out, reach out if you have any questions, and I hope that lesson made sense. Take care. We'll see you in the next one.